All right, time to talk about finite difference solutions to the one-dimensional consolidation problem. So in Terzagh's solution, he assumed that this C sub v coefficient of consolidation is a constant, but in reality, the compressibility and the permeability, which go into defining C sub v, are not constant. As you recall, the definition, CV is equal to K over gamma W times 1 plus E over A sub V, right? So if we look at this, K is a variable that evolves, A sub V is a variable that evolves. Gamma W is a constant, right, the unit weight of water. And then technically void ratio also evolves during consolidation, right? So 3 of these parameters are actually changing, which may have an impact on the computed C sub V value. So for compressibility, the A sub V constant, let's take a look here. We've got E versus log sigma V prime. And we have a normal consolidation line in CL that has a slope of C sub C and then an unload reload line with a slope of C sub R. Let's just say, for example, that we're on the normal consolidation line and we have a point on the normal consolidation line, a reference point, E ref and sigma V prime ref. That can be any point on the line. It's just that we need to know one point on the line in order to write the equation of the line. So here's the equation, right? E is equal to E ref minus CC log of sigma V prime over sigma V prime ref. All right, now C sub C is a material constant, right? It does not evolve during consolidation. And what we can do now is take the derivative, minus dE d sigma V prime. And that's the definition of AV, right? So we can compute A sub V easily. Right there, that's equal to AV. And that comes out to be C sub C divided by sigma V prime times the natural log of 10. That's if OCR is 1, if we're along the normal consolidation line. Or alternatively, you can just substitute CR into that equation if you're over-consolidated and going along that line. So if OCR is greater than 1, A sub V is just CR divided by sigma V prime natural log of 10. So even if C sub C or C sub R are material constants, and we're either staying normally consolidated or staying over-consolidated during a particular load stage, we see that A sub V is not constant, even under those loading conditions, because it depends on sigma V prime, which is a variable, right? Sigma V prime increases during consolidation if we're loading the soil. Therefore, A sub V is not a constant, because sigma V prime changes. So we can use Terzagh's solution, but we have to recognize that we're making assumptions that don't match reality here. Okay, we can pick A sub V to be reasonably representative of a field loading condition, but it's not going to perfectly match the soil behavior for all of the different load levels. Okay, and then of course there's another potential source of nonlinearity in A sub V. Let's imagine we start over-consolidated and then we come and turn the corner, right, at a particular, say that this is at a particular depth within a layer, right, where maybe the OCR is 2, and then we come to past the previous sigma P prime value and come down the normal consolidation line. Well, now, as loading progresses, A sub V starts according to this equation, and then it suddenly changes to this equation during loading. So that's another source of nonlinearity that is fairly complicated for us to try and handle, and certainly is difficult to incorporate into Terzagh's 1D consolidation solution. Okay, permeability, also not a constant. So people have done a lot of different permeability tests on different soil types and have found that the logarithm of permeability is approximately linearly proportional to void ratio, such that at low void ratio, the permeability is lower. Right, soil particles get closer together, the void space becomes smaller, and it's harder for water to flow through the soil. So an equation for this type of behavior is E is equal to E ref plus CK times log of K over K ref, where E ref and K ref are just, again, any point on this line, right? So we can define a line that gives us permeability. So if we wanted to do a problem where compressibility and permeability change, as loading progresses, we can't really use we can't really use analytical solutions anymore because the differential equation becomes too complicated. So instead we switch to numerical solutions. And a solution that works pretty well for this problem is the finite difference method. pretty straightforward. I just wanted to go through and derive the equations for you here, just to show you kind of how easy it is to do this. It may seem a little scary to be doing a numerical solution and writing code and that kind of stuff, but I'll show you that you can actually do this using a spreadsheet solution if you want. My preference is to do a real code solution, but you know, at least the forward Euler method can be done using a program like Microsoft Excel. So the calculations we're doing are not super complicated here. All right, in the finite difference method, we have to discretize the layer in space and in time, both, right? So in space, we have some number of nodes. You can think of it as nodes and elements, although we're not really doing elements here since it's just a finite difference method. But anyway, you could think of it that way. So here I'm using I as the index counter for the nodes in the depth dimension. So here this would be 1, 2, 3, 4, and then you go all the way up to n, where capital N is the number of nodes that we've chosen to discretize the domain into. Usually this is quite a few. We're not going to use 8 or 10 like we do for a solution of the amount of consolidation, because 8 or 10 just doesn't give us the accuracy we need to solve this problem numerically. So this would be tens or maybe hundreds, depending on the problem, of nodes. And then similarly, we discretize time, right? So we start at 0, and then, you know, if we have a constant dt, it just goes 1, 2, 3, 4, all the way up to some number of time steps. And I'm going to use j for time. So I is the index counter for depth, and j is the index counter for time. All right, now here's how we do the finite difference solution. What we want to do is solve for the second derivative of u with respect to depth. So here I've sketched out a curve that might be a given, you know, just some kind of solution. It's a schematic. And we have different nodes. There's the I-1 node, there's the I node, and there's the I+1 node. And what we want to do is find the second derivative of this function at point I. And the way we'll do that is to approximate it as the difference in slope. So this slope du2 dz right here between I+1 and I, minus the slope from I to I-1 divided by the depth interval dz, right? So it's like the second derivative is the difference in first derivatives over the element length, right? So here's the equation for the approximation of the second derivative of u. I+1 comma j-1 minus ui comma j-1. So that's this slope right there, right? Minus, oh, and then, of course, divided by dz, which is that height. And then minus u of I, comma j-1 minus u of I-1, comma j-1 divided by dz. So it's that slope. This slope minus that slope divided by the element height. So that's our approximation. And if we simplify terms, we get this expression for the second derivative, right? Pretty straightforward to derive this equation, very simple equation. Okay, notice that I'm using j-1 for the time vector. All right, I'll explain this in a little while, but what I'm doing is an explicit method, the forward Euler method, which means that basically we're projecting into the future what's going to happen at the next time step based on what the current state of the model is at this time step. All right, so the reason why it's called explicit is that we can come up with an explicit equation for u of I comma j this way. We don't need to do any kind of system of equations that would involve an implicit method like the backward Euler method, which I'll talk about in the next video. Okay, so we're using j-1, which means that we have to know the very first time step, right? We have to know the initial condition. Then we can solve for what happens at time equals j equals 1, right? Time equals dt. Okay, now let's go on to the discretization in time, which is actually even easier than the one in space because it only involves a first derivative instead of a second derivative. So here we see there's a slope du dt between time j and time j-1. So du dt is approximated as u of I comma j minus u of I comma j-1, right? So this is at some node zi, right? Whereas up here, this was at time t j-1. So that's how we've chosen to formulate this problem. All right, so we end up getting C sub v, and this is C sub v at a particular node at time j minus 1, right? So we're allowing for the possibility that C sub v may change as a function of depth and time here. It could just be a constant, in which case we could technically get rid of the index values, but we'll assume that it's a variable. So C sub v times the second derivative of u with respect to z is equal to du dt. And now everything is j minus 1 except for this term right there. So we can isolate that term and we get u of ij is equal to C sub v ij minus 1 dt over dz squared. And then we have the second derivative terms there, and then the previous value of pore pressure at time j minus 1 here. So this term gets added on to that term. Okay, now here's the initial conditions, right? We need, since we're having a j minus 1 here appear in a lot of places, we can't use this equation to solve it for j equals 0, right? For that very first time step. We just have to know that as a boundary condition or as an initial condition. So here's the boundary conditions we need to know to solve this problem. Okay, first of all, u of I comma 0. This is the values at time equals 0 is equal to delta sigma v, right? Or du. We're assuming that the change in vertical total stress is equal to the change in pore pressure. So at time 0, all of them are equal to delta sigma v. And then we also know, because of drainage boundary conditions, that the top node always has 0 pore pressure, and the bottom node always has 0 pore pressure, right? Those are the drainage boundary conditions. This is the initial condition. Okay, now let's look at what we could do if we wanted to solve this using a spreadsheet solution like in Microsoft Excel or something like that. Well, the first thing we could do is create a row for all of the time steps and a column for all of the depth intervals. So this is going to be a pretty big table, right? Because maybe we have 100 depth intervals and maybe we have, 1,000 time steps or something like that. Well, then we can put in the first column, right? Because we know that the first column involves zeros at the top because of the drainage boundary conditions, and then delta sigma v's everywhere else until you get to the very bottom where it's again 0. So again, that first row is 0, delta sigma v all the way down, and then 0 again at the very end. Then we go to the next time step 1, and now this is where we're using our equation. Okay, again, we know that 0 has to be the pore pressure at the top and at the bottom, and then all these other cells in column 1 we can calculate using our finite difference equation. So u of 1 comma 1 is equal to cv at 1 comma 0 dt over dz squared. And then we have the value u2 comma 0, so we're using this value, minus 2 times u of 1 minus 0, which is that value, plus u of 0 comma 0, that value, plus the initial value here, the previous value there, delta sigma v. Okay, so you can just drag that down, and then you go and do this one, and you're going to be using column 1 now to compute values in column 2. So you can just march along and do this thing, kind of drag and drop, no problem. Okay, now let's talk about this. We have used CV of I comma j minus 1, and we formulated the second derivative of pore pressure with respect to depth in terms of the j minus 1 time step. That means that we've been using the forward Euler method. In other words, we're going to project the next time step based on the values at the current time step. That's an explicit method because we were able to get an explicit equation for u of I comma j. Now, this method becomes numerically unstable if we exceed a certain ratio of CV dt over dz squared. Okay, if this value becomes larger than a half, the solution will become numerically unstable. And I think we can kind of see why that might be the case if we have, we're approximating some curve like this, right? And let's say that we're going from here to there, and that's the actual solution, right? I'm not labeling the axes here because it doesn't really matter. This is just a concept. Okay, if that was the actual solution, what the finite difference solution, the forward Euler solution would give us is that we would use this slope, right? And we would approximate the solution as being right there. So that this distance is an error, epsilon. Okay, well, if the guess, well, and then we would evaluate the gradient at this point, and the next slope would be this way. And so we're gradually walking away from the actual solution, and those errors accumulate as they go. Okay, and then you can end up with some kind of non-physical answer if these errors become too big. So in order to keep the errors small so that the forward Euler method is stable, we have to keep this ratio, CV dt over dz squared, less than 0.5. So let's call that variable alpha. A lot of the time it's called alpha, CV dt over dz squared. So the way you would do this problem to ensure numerical stability is that you wouldn't independently specify dz and dt because you might pick a combination that violates this ratio requirement for alpha. So what we would do instead is define define dz, right? This is how we want to discretize with depth. And then we know CV. Let's assume that CV is constant just for the sake of computing this ratio. Then we can specify alpha, right? We know that our solution will be stable as long as alpha is less than a half. A lot of the time we use 0.25. So you could put in, 0.25 for alpha and then solve for dt. And now you know that you're going to have a numerically stable solution using this finite difference method. We will go to the backward Euler method in the next video. That's where you use the slope at the end of the time step rather than the beginning of the time step to march through the solution. It is unconditionally stable, so you always get numerically reasonable results. But in general, the solutions, whether you're using forward Euler or backward Euler, solutions become more accurate as you decrease the vertical spacing and as you decrease the spacing in time. So we want to be careful about picking enough depth intervals to get a reasonable solution.